Swayam Prabha. Digital India. Educated India.
So up till now, we have assumed that a program perceives the entire memory system to be its own. So if every program on a 32-bit machine, how large is the memory system that it can potentially address? Well, so if the addressing is 32 bits, we can address all the bits with, all the bytes with addresses 0 to 2 to the power 32 minus 1. So that's the total number of bytes that we can address. Because mind you, one location contains only one byte. So total we can address 2 raised to the power 32 bytes, which is 4 times 2 raised to the power 30, which is, so 2 to the power 30 is 1 gigabyte. So this is 4 gigabytes. So 4 gigabytes is the total amount of memory space that we can address. And within this, we can access any location at will. So this is the assumption that we make, all right, that the entire memory system is ours. We also need to take multiple programs into account. So, for example, at this point, maybe 100 programs are running on my machine. So my CPU runs program A for some time, then switches to program B, and then to program C. So in a sense, it's called a time-shared system, where we run one program for some time, one more program for some more time, and one more program for some more time. So the question is that do they corrupt each other's data? The answer is no. So for example, if I have programs A and B, and let's say I run program A for 1 second, and then I run program B for 1 second, does A deliberately write into the memory space of B and corrupt its data? The answer is no. And does B deliberately write to A's data? Deliberately or non-deliberately, just like that. Inadvertently, does B write to A's space? The answer is no. So somehow we are able to achieve a partition of the memory regions used by A and B. But again, how is this possible? Because A assumes that the entire memory space is its own, and B assumes the entire memory space is its own. So if A writes to, let's say, location 20, and B writes to location 20, then they will end up overwriting each other's data, which is exactly what we don't want. So this is also called the overlap problem, and this is something that we want to solve, that we have to ensure. So this aim over here is a good aim, that both A and B actually should think that they are the owners of the entire memory system. However, in practice, we need to ensure that they don't overwrite each other's data, right? So this is aim 1 for us. So let's call it aim 1. Then there is an aim 2. If we consider physical memory, so what is physical memory? Is the total amount of physical storage that we have, right, in the main memory. That's the physical memory. So if we consider a memory system that has less than 4 GB of physical memory, so let's say it has 2 GB of physical memory, right? We need to ensure that all our programs still run. So if a program accesses a location which is, let's say, after 3 GB, it should still run on this system, right? So this is something that has to be ensured, that even if the size of our physical memory is the actual amount of memory that we have, right? In terms of DRAM chips and so on. So these actual transistors that we have. So if this is 2 GB, which is less than our virtual memory space, which is 4 GB, which is the entire space that can be addressed, we need to find a way of ensuring that programs work. So this is also called the size problem. So two problems, size and overlap. So let me just redefine these two concepts. Physical memory refers to the actual set of physical memory locations that are contained within the main memory, right? So the main memory is a set of uh, memory chips which contain DRAM cells, and so this is the actual physical memory. And of course we have the caches as well, but if we consider an inclusive cache hierarchy, then essentially the size of the physical memory is the size of the main memory. And this can be, anything. It depends upon the amount of hardware that we have invested. But virtual memory is what the program thinks it has. So physical memory is what you actually have, but virtual memory is the amount of memory that a given program or a given programmer thinks that you have. So it's the memory space assumed by a program, which is assumed to be contiguous and without limits. And let's say if a memory address takes n bits, then the total virtual memory size is 2 raised to the power n. In other words, if let's say it's a 32-bit addressing that we are using, then the total virtual memory size is 2 raised to the power 32 bytes or 4 gigabytes. Similarly, if we are using 64 bits, then the total virtual memory size is 2 raised to the power 64 bytes, which is huge. So which is essentially 16 times, roughly 16 times 10 to the power 18 bytes, which is massive. All right. So essentially the idea here is that, we are defining two concepts, and the concepts are again different. Physical memory is the actual amount of storage, and virtual memory is the amount of storage that you think that you have, right? So both are different, right? One is an ideal dream world, the virtual world, and the other is the actual world where you have actual storage devices. And the two problems that we need to solve is space and overlap. So overlap means that two processes A and B do not end up, overwriting each other's data, even though the physical memory is shared between them. And the space problem is that, your physical memory can actually be less than the amount of virtual memory that you have. In that case, your program should still work. So we need to find out how to enable that. So let us look at a process, the virtual memory map of a process in a Linux operating system. So recall that a process is a running instance of a program, right? So all programs, so this is the ELF format, so all programs actually start with the virtual address 0. So from 0 till a certain address, right? From 0 till a certain address, we have the header. The header is basically, so it records the type of the program, the type of the encoding. So there is a lot of meta information in there. Then we have the text section of the program, which is actually the instructions of the program. So they pretty much start from this virtual address. So after having all the instructions of the program at the data section, which consists of static variables and global variables, static oblique global variables with initialized values. So let's say in the beginning of a program, I define int x equals 10. Since this data is initialized, it will come to the data section. We then have a BSS section, which also contains static oblique global variables, the same thing, which are not initialized. So that's the reason they are all filled with zeros. Right, so anything that is not initialized is filled with zeros. So that is the BSS section. So this is how one part of the virtual memory map is divided. And if I look at the top, so at a very high address 0xc and then 7 zeros is when the stack starts, right? And since the stack is downward growing, it grows towards lower addresses. And similarly, after the BSS section, the heap starts. Recall that the heap is a memory area where we put in dynamically allocated data, like the data that is allocated with calls like malloc in C and new in C++ and Java. So all the data will go on the heap. In the middle, we have a segment called a memory mapping segment. This is fairly complicated, so I will not be discussing it. But if you want me to give a one-line summary, the one-line summary is as follows. That let's say if I open a file or something, right? A file or a disk, a file on a hard disk. So, but we have not discussed what is the hard disk. So I sort of, ask readers to take this with a pinch of salt. What we can do is we can assign a memory region that corresponds to something that we are, trying to open, like a file, right? So if I have a certain movie file, then if the movie file is stored somewhere else, I can assume that this region has a one-to-one correspondence with the bytes in the movie file. This is all that I can say at this moment. I really don't want to go deeper. However, after getting an understanding of virtual memory, we will be in a position to discuss this in some more depth in chapter number 12, the last chapter, right? We'll discuss memory mapping, but let's leave this for the time being. Alright, so basically what happens, every single process has a roughly similar memory map where we start from address 0, first have the header, then the text, then the sections to store global / static variables, and we have spaces for the heap and the stack. So something that can be deduced here very easily is that most of these, so let's say the stack, the addresses will be common across processes. So how come they will not overwrite each other? So we'll discuss solutions to this problem. But before we do that, let's take a look at some memory maps across operating systems. So basically, if we consider 32 bits, the total virtual memory size is 2 to the power 32, which is 4 gigabytes. So what the Linux operating system will do is that it will give 3 gigabytes to user programs, the typical programs that run, and it will keep 1 gigabyte for the operating system itself. This is the first time that we are hearing the word operating system. So the operating system is a special program whose job is to manage other programs. The Windows operating system, what it does is that it does a 50-50 split. So it gives user programs 2 gigabytes, in the 32-bit version, and it gives the OS, the operating system, called the OS kernel, 2 gigabytes. So this is a minor difference. So let us now look at the main idea of what a virtual address is, right? Of what virtual memory is. So if I consider a program, right? All the addresses inside a program are virtual addresses, where I assume that the entire memory space belongs to me. And I can access, and the way I split the memory space is this way, between header, text, data, BSS, heap, and stack. Alright? But mind you, here again the assumption that is being made is that the entire space is available to one process. So this is the virtual address that we use. However, this is not the address that goes to the memory system. So if I consider this as the memory system, the address that goes to the memory system is actually something else. It is the physical address. So between the virtual address that a program uses, a compiler uses, and the physical address that is sent to the memory system, we need to have an address translation system. So this is called with different names. It's also called the memory management unit, the address, the virtual to physical address translator. So call it by any names, any name, we'll call it the address translation system. It basically, it converts one, in our running example, one 32-bit address into another 32-bit address, and it sends it to the memory system. Now if I consider one more program, so let's say this is program A and this is program B. I'm sorry. So program B will have one more address translation system of its own, which is again, different. And this address translation system would again yield a physical address, because mind you, the physical address is not different. The physical address is the same because it corresponds to an actual location, right, in the caches or in the main memory. So anything inside the processor is a virtual address. Anything that goes out of the processor to the memory system, including the L1 cache, right, is the physical address. And for every program that's running, it will have its address translation system. We'll discuss this in great detail, which converts a virtual address that the program uses to an actual physical address. And the physical address is the same for all programs because it's corresponding to an actual location. And the virtual addresses don't matter. And also, the aim of the address translation system is to solve both of our problems, which are essentially the overlap problem, ensuring that A and B don't overwrite each other's data, problem number one, and to ensure that the size problem, which is that if the physical memory is less than the virtual memory, right? We don't have enough physical memory, then how to take care of this situation. These are the two problems that the address translation system must solve for us, right? And so that's the reason we have virtual memory on one side of the translation system, which is what the program thinks it has, right? The entire memory space, one large contiguous memory space, and the physical address, which is on the other side. Both are separated by a translation system. So to describe the translation system, it's not possible to do in one slide. It'll take multiple slides. So let's use the multiple slides and describe the translation system in some amount of detail. So let us divide the virtual address space that we have, right, the total memory space that a program thinks it has, into chunks of, contiguous consecutive chunks, the same way we had blocks in a cache. We divide the address space into chunks of 4 kilobytes. And each such chunk is called a page. Alright, so each such chunk of consecutive 4 kilobytes is called a page. And similarly, we divide the physical address space into again contiguous chunks of 4 kilobytes. This is called a frame. So mind you, the virtual address space and the physical address space can have different sizes. For example, it is very much possible in modern processors for the virtual address to be a 48-bit quantity, and maybe the physical address to be a 36-bit quantity. That is perfectly fine. Your address translation system will map a 48-bit quantity to a 36-bit quantity. No problem in that. All that we are saying is that let's take this address, same way we made cache blocks, right? The same way we had atomic indivisible cache blocks. Let's make a larger block. Let's call it a page when we are creating blocks out of the virtual address space. And let's call it a frame when we are creating blocks out of the physical address space. So the job of the translation system is to map a page to a frame. So let us consider this number in some more detail. 4 kilobytes, right? 4 kilobytes is 4 is 2 square. And a kilo is 2 to the power 10. 1024 we are approximating to 1000. So this is 2 to the power 12 bytes. And so it will take 12 bits to specify the address of a byte within a page. So what we can do is, given an address, we can, let's say given a 32-bit address, what we can do, so let's consider 32 bits because it is a running example, but we can easily extend it to other memory systems. So we'll take the bottom 12 bits, right, which is essentially the offset of a byte within the page, and discard them. The remaining 20 bits are the page address. These 20 bits need to be mapped to another physical page, which is a frame. So we'll discuss about this in some amount of greater detail in the next slides. But let's look at the main insight. Well, the main insight is that, why are we making the blocks? Well, the reason we make the blocks is as follows, that it will reduce our translation overhead. So instead of, doing a translation for every byte, we can actually translate it at a much higher granularity. So it will save us some effort. So first is that the page is really large. Let's say it's like 100 megabytes. Then, most of the page will actually remain unused. And since we will not divide so a page size and frame size, mind you, have to be the same. So since we are not dividing a physical page, since we are not dividing a page or a frame into multiple subparts, If we have a really large page, we might end up wasting memory. Similarly, if the page or frame size is very small, let's assume that it is only like 8 bytes. Then we will have the overhead of mapping will be extremely high, right? So we'll have to map very frequently. So that's again a bad idea. So 4 kilobytes has been experimentally been found to be a good choice. So we take 4 kilobyte chunks, and for each of this we map each page to a frame. So let me discuss in some more detail. So the mapping process is as follows. Let us look at a diagram, of course not drawn to scale, of the virtual memory regions that program A, process A uses. So let us assume that the entire blue is the entire virtual memory region of process A. So mind you, the diagrams are not drawn to scale. So out of this, light blue is the regions that are not used, right? So basically they are not accessed. And the darker blue is the color of the regions that are accessed. So in these regions, we divide the regions into 4 kilobyte pages. So each such square box is a 4 kilobyte page, right? So this is a 4 KB page. So each page is mapped to, so basically if you consider process A, it sees a contiguous virtual memory where the virtual memory occupies the entire memory space, and it does not need to see any other view. But what happens in the middle, sort of the secret sauce, is that there is a mapping layer that the program does not get to see, and that's the secret sauce over here. So essentially every page is mapped to a frame. So this is the crux of the idea. Every page is mapped to a frame. But mind you, this page is mapped to this frame. This page is mapped to this frame. This page is mapped to this frame. And this page is mapped to this frame. So they are pretty much mapped to random frames which are dispersed all over in physical memory. And the frames are definitely not contiguous. And the greatness of this mapping is that the programmer, the process, the compiler can see the virtual memory as one nice contiguous memory. But what happens in reality is that each of these pages get mapped to different frames, and the different frames can be there all over, right? So they need not be contiguous. So this solves most of our problems. The reason is that let's again take a look at both of these rectangles. So let's consider the virtual memory of program B. So let's assume that program B addresses memory in 2 regions where each region fits within a page. So again, these pages are mapped to different physical frames, which of course are totally disconnected. So but the interesting way in which the overlap problem is being solved is like this, that if you see, we are not allocating a physical frame to pages belonging to 2 separate processes, right? So for example, this physical frame is only allocated to this page. So this page and this physical frame have a one-to-one correspondence. Similarly, this page and this physical frame have a one-to-one correspondence. So we never allot the same physical frame. So we never map it to pages in 2 separate processes. This ensures that there is absolutely no overlap, right? So this is exactly what solves the overlap problem. And the way it solves the overlap problem is that the programmers, the compilers can have their own view. In reality, there is a thin memory mapping layer which is not visible. That's a part of the processor's secret sauce. And this is where the address actually changes. And from the page address, we go to a frame address. The frames can be dispersed all over. For example, when we move from the last byte of this page to the first byte of this page, as far as the programmer is concerned, we are only moving ahead by 1 byte. But what is actually happening in reality is that this page was mapped to this frame. So the last byte of this page is the last byte of this frame, which is essentially this byte. Then again, when we move here, the mapping changes, this page gets mapped to this frame. So basically this byte, which is the starting byte of this page, actually gets mapped to this byte in a physical frame. So the advantage here is that both A as well as B can see the entire memory space as their own. There's no problem. But since they will not be occupying the entire virtual address space, which is 4 gigabytes, but they might be occupying, let's say, 10 kilobytes, 100 kilobytes, 1 megabyte, we can divide the memory region into pages where each page is 4 kilobytes. And because of spatial locality, we'll have a nice clustering of data. And these pages can then be mapped to frames in memory. The only constraint here is that one frame has to be mapped to only one page. So for example, mapping this frame to this page and mapping this frame to this page is not allowed. Right, if it's done purposely, that's a separate issue, but otherwise it is not allowed. This ensures that two processes can never share data in the physical memory. So this solves our overlap problem. So this slide is very, very important, and just in case you don't understand this, I would advise the readers to take a look at this and sort of take the video back and go over this as many times as possible, because this diagram is the crux of virtual memory. If this diagram is understood, all of virtual memory is understood. And if this diagram is not understood, pretty much nothing is understood. So students should make utmost effort to understand this diagram. Let me again summarize what this is doing in 2 sentences, but to risk loss of interest due to repetition, I'll move ahead. What we are trying to say is, let processes A and B perceive a nice contiguous memory system. In reality, we take the regions that they access, block them, group them into pages, and map each page to a frame in physical memory that has the same size. And we never share a frame across 2 separate processes. That will solve the overlap problem for us. There are other problems. Let's take a look at it. So also the size problem can be solved like this, that if the virtual memory size is 4 gigabytes and this is only 1 gigabyte, it makes no difference at all, because in any case we have broken this down into frames and we just have to map pages here to frames. So it does not, so the actual size of this does not matter. It will only matter if the working set of programs A and program B, the amount of memory they require, exceeds 1 gigabyte. Then the entire physical memory will fill up. But that is rare. So typically programs don't use that much of memory. So that's the reason we are safe. Alright, so now let's take a look at the details of page translation. So given a virtual address in a 32-bit addressing scheme, since a page is 4 kilobytes and 4 KB is 2 raised to the power 12 bytes, the lower 12 bits will specify the offset of the byte within the page, same way as the offset of a byte within a block in a cache. So this part can be ignored, right? For both this part is the same, right? It's the same. So basically, this is the same as this. So as a result, we can ignore these two. But what will, however, change is the upper 20 bits, which is the page number. That will go to the translation system, and what will come out is a 20-bit frame number. So the translation system is also called the page table, because for every page, a page number comes in and a frame number comes out. This is also called the page table. So in the virtual address, 20 bits come in, 20 bits of the virtual address come in, and 20 bits of the physical address come out. So let's take a look at a very simple and naive implementation of a page table. So this is called a one-dimensional page table, which is very simple. We enter 20 bits. So 20 bits, how many combinations we can have? It will be 2 raised to the power 20, which is 1 million. So roughly, 1 million combinations we can have. And then each of these entries will have a 20-bit frame number. And so what we do is that we will, like a direct mapped cache, we will access one entry, read the frame number from it, and give it as the output. So let's look at the issues with a basic single level page table. So the size of the single level page table can be computed as follows. So the size of a single entry is 20 bits, 2.5 bytes. The number of entries is 2 to the power 20 or 1 million. The total amount of storage used is 2.5 megabytes. Now the page table is specific to each process. So if we have 200 processes running instances of programs, as is the case that is currently happening on my system, we will spend 500 megabytes, half a gigabyte, in just storing page tables, which is not acceptable. It's a huge amount of memory space that is being used to store page tables. This is just too much. So what is the insight? Well, the insight is that most of the virtual address space is actually empty. For a given program, the virtual address space that it's talking about is around 4 gigabytes. But out of 4 gigabytes, the amount of memory a program might be using might only be 10 megabytes. Right? The rest is empty. So they'll not require that much of memory. So maybe we can leverage this pattern in some way. So let's see how it can be leveraged, used. So let us consider a two-level page table. This is called a multi-level page table. So what we do is that we divide the page number, which is a 20-bit quantity, into two 10-bit quantities, 10 and 10. So we take the most significant 10 bits, right, the upper 10 bits, and we use it to address a table which has 2 raised to the power 10 entries, which is 1024 entries, right? So this is called the primary page table. Subsequently, the primary page table, so mind you, since a program does not access a lot of pages, most of the entries in the primary page table will be empty. So I'll discuss this in some more detail towards the end of this slide, but let's just continue with the discussion. Each of these primary page tables points to a secondary page table. So let's say this entry points to this secondary page table. We take the remaining 10 bits and use it to address the secondary page table, which again has 2 to the power 10 entries. And each entry of the secondary page table contains the 20-bit frame number. This design, right, where we take 10 bits, first access a primary page table. The primary page table contains a pointer to the secondary page table. Then we take the next 10 bits and access the secondary page table. This design is called a two-level page table. And the claim is that it's a far more efficient design. Let's see why. So we have two page tables here, so there has to be some advantage. And let's see what is the advantage. So the first advantage is that, the way that we do this addressing. So if you consider a 32-bit memory address, and we divide it into 10 bits, 10 bits and 12 bits, right? So anyway, the bottom 12 bits correspond to the address of the byte within the page, so they're not important. The upper 10 bits, the most significant 10 bits, which are these bits, are expected to have the least amount of variance, right? So if I consider, so let me look at it in some other way. Assume that I'm counting from 0 to 1000. So then the first number, in decimal, first number is 000, then 001. After some point, I'll reach 201, 202, this way. So where do I see the least amount of variance or a larger amount of predictability? I see the least amount of variance in the most significant digit, right? The most significant bit, byte, digit, doesn't matter. And I see the highest amount of variance in the least significant digit because it changes very frequently, right? So this is where I see the highest amount of variance, right? So we put a plus plus here and a minus minus here. The same is true for memory addressing. So typically when I'm accessing an array or reading instructions in a program, I would expect the maximum amount of variation, in the bits to actually happen for the lower 10 bits of the page number, and I would expect a relatively lower variation to happen in the upper 10 bits. And then look at this counting example. So essentially the upper 10 bits remain relatively stable, and they change only once every 100 entries, but the lower bits change far more frequently. So if I take these upper bits, so most likely very few of these upper bits will point to valid entries, right? And most of the entries here will actually be empty because no combination of upper bits would actually point to them. So this is a good strategy. So this minimizes the number of secondary page tables that we need to use. In this case, if our upper bits only point to 3 separate entries, so mind you, the primary page table is a direct mapped cache. So if the upper bits point to only 3 valid entries, we need to allocate only 3 secondary page tables, right? So this is allocated on demand. It is not that we allocate all 1024 secondary page tables. That will defeat the purpose. Only the number of secondary page tables that are required are allocated. So in this case, only if 3 of the entries in the primary page table actually get pointed to by the upper 10 bits, more significant 10 bits, we allocate only 3 secondary page tables. Then we use the remaining 10 bits to address them. If you want me to do some math, then the math is like this, that each secondary page table contains 1024 entries. Each entry is 20 bits or 2.5 bytes. So the total memory requirement of a secondary page table is 2.5 kilobytes. So 2.5 kilobytes will roughly map 4 megabytes of virtual memory. And of course, we'll allocate only those many secondary page tables as required. So let's consider, so we have already talked why this is a good idea and keeping spatial locality in mind. Let's consider an example. If a program uses 100 megabytes of virtual memory and needs 25 secondary page tables, we need a total of 2.5 kilobytes times 25, or 62.5 kilobytes for saving secondary page tables. And we'll also need a little bit more, at max. We'll also require this much of space for the primary page table. So the total amount of storage, right, can be this or can be slightly more. But in any case, it is approximately 62.5 kilobytes, plus or minus a few, or not minus, but plus a few more kilobytes for the primary page table. But this is minimal, this is absolutely minimal. It's, roughly 60 odd kilobytes per process as compared to 2.5 megabytes per process. So, in one, per process, if I consider a one level page table, we were spending 2.5 megabytes. If I consider a 2-level page table, we are spending 62.5 KB. So this is clearly space efficient by an order of magnitude. That's the reason secondary page table should be used. What again is the insight? Well, the insight is simple. The insight is basically that we do our addressing in this manner, that we divide the address into 2 parts, and the upper part is expected to show little variance or randomness. Recall our counting logic. So very few of these entries would actually be populated and point to valid secondary page tables. And we'll not allocate a secondary page table for every entry. So let's say if this has 1024, but maybe if only 10 secondary page tables are required, we'll allocate space for only 10. And each of these secondary page tables is 2.5 KB. So the total space utilization is very small, very modest. So that's the reason 2-level page tables are used in almost all commercial systems. Let us now look at a different kind of a page table called an inverted page table. The inverted page table per se is not very popular, but it still has a very strong motivation. So the strong motivation for using an inverted page table are as follows. That let's say the size of one page table is 50 kilobytes, right? So since a page table is specific to each process, and let's assume that there are 100 processes in the system, then the total amount of memory that is used is 5000 kilobytes or 5 megabytes. For certain systems that are memory constrained but still have a lot of processes, it is kind of difficult to find, this much of memory to save page tables. So that's the reason. Also, updating. So when processes, there's a context switch. One process leaves the CPU and another process starts running on the CPU. The page table needs to be changed. So, given the fact that we have these overheads, it's a better idea, at least perceived by some, to have an inverted page table. But again, the two-level page table, in the previous slide is far more popular, but this is still used notably in some IBM machines. So the idea here is that we have a single page table where the entries of the page table are essentially, they correspond to each physical frame in memory. So we can logically think of that we are giving a 20-bit frame number as input. So it'll have, somewhere like 2 to the power 20 entries. And, each entry will store the page number that this actually corresponds to. And the page number and the process ID, which page number belonging to which process. So depending upon the math, this can technically work out to be a slightly more space efficient solution. So if you consider, let's say this particular design, and if you assume that each entry is 20 bits, which is 2.5 bytes, so the total size of this is 2.5 bytes times 2 raised to power 20, which is 1 mega. So this is 2.5 MB. So if we have 100 processes, then we see that with traditional page tables, it might take 5 megabytes. If we assume 50 kilobytes per process, which is kind of reasonable, and this takes 2.5 megabytes, and if we have even more processes, then this approach will be more space efficient. And here we have one entry per physical frame. For each entry, in each entry, we save the page number and the process that this entry is mapping to, right? This page belongs to. So all of this is fine from a conceptual point of view, but the way we implement it is slightly more complicated. So in this case, we consider the 20-bit page number and we consider the process ID. So the process ID, this depends upon the number of processes that we wish to support. So in a system with 1000 processes, we will need 10 bits. So the total size of this, 20 bits plus 10, the total size of this is 30 bits. And so we need to take the 30 bits and pass it through an hashing engine. So hashing is a very common term in computer science. So for those who don't know what a hashing engine is, so let's consider this as a hashing engine. And let's assume that 30 bits are going in. So what a hashing engine does is that it mangles the 30 bits and computes another number which has a fewer number of bits and which is pretty much decided randomly. So, these numbers, the output has a uniform distribution. So what this means is that I can think of this as a black box where 30 bits come in and 12 bits come out, which means that for every 30-bit number, right, for every 30-bit number, there is a unique mapping to a 12-bit number, right? So basically, given a 30-bit input, there is a 12-bit output. So mind you, for every output, multiple inputs might be corresponding to it, but for every input, only one output corresponds to it. So if we assume that the input here is 30 bits and the output here is 12 bits, so typically hashing engines are considered uniform. A good property is called a uniform hashing, which means that all the outputs are equiprobable. So it sort of balances the inputs across the outputs. But that again is a pretty theoretical concept. But what we are concerned with is that 30 bits are coming in and 12 bits are coming out. So we use these 12 bits to access a table called a hash table. So since we have only 12 bits, the maximum number of entries that we can have in this table is 2 raised to the power 12. So let's say this maps to this entry. So each entry of the hash table maps to one entry of the inverted page table. So let's say this entry maps to this entry. Right? So it's not so we can discuss more about this mapping, but let's first look at, go over the figure at least once. So each entry in this hash table maps to one and only one entry in the inverted page table. So we first compute the hash, access the entry in the hash table, then access the entry, from here we access the entry in the inverted page table. And so I'm sorry, in this example, it's not this entry that's mapping to, it's actually this entry that is mapping to. And in this entry, we look at the page number and the process ID that is stored in this entry. So pretty much every entry in the inverted page table stores the page number and the process ID, right? So we compare our page number and PID with the number that is stored over here. So let's assume that it does not match. So why will it not match? Because multiple inputs can get mapped to the same 12-bit number, to the same output of the hashing engine. So as a result, they'll come here and all of them will be redirected to this entry. So if there is no match, let's do one thing. Let's then search in the next k entries, right? So k can be 1, 2, 3, 10, doesn't matter. So in this case, it's 3. So let us search in the next k entries and check each one of them. If there's a match in any one of them, well, we are good to go. Otherwise, we will infer that this entry is not there in the page table. So once, let's say this entry matches, so then this will also store the frame number and we read out the output frame number. All right. So let me just go over the entire slide once again after erasing the ink. So the idea here is that we first construct a number out of the page number and the current process ID, which we have assumed to be 10 bits. Given the 30-bit number, we send it to a hashing engine, which mangles the bits and complicates it and computes a complicated function, where the output will typically be a smaller number that is maybe 12 bits wide. Right? That's the example that we have been using. We now use these 12 bits to index a separate table called a hash table, and each entry of this hash table points to an entry in the inverted page table. So let's say we come to this entry, right? So from here, let's say this entry points to this entry in the inverted page table. Here we compare the process ID and the page number that are stored over here with our process ID and page number, right? With which we access this. If there is a match, well and good, we read out the frame number that is stored in this entry. Otherwise, we search over the next k entries and we read out the frame number. So the advantage is we have one page table for the entire system. Also, a smart reader would ask, what is the necessity of having this hash table? Why didn't we use the hashing engine directly to access an entry in inverted page table? Well, so the answer is like this, that maybe there are some frames that we don't want to assign to any process. So maybe, these two frames over here, we don't want to assign to any process. We sort of want to reserve them for either the operating system or for some other special kind of process. So to, achieve this, what we should do or what we need to do is that we need to add a further level of indirection where we first actually access the hash table, and entries in the hash table will point to entries in the inverted page table. So for example, if you want that this entry will not be mapped to any page, then we basically need to ensure that no entry in the hash table will actually point over here. Had we not had the hash table, then, and since the hashing engine produces these 12 bits which are uniformly distributed, Definitely for some input combination, we would have mapped to one of these entries that we don't want to be mapped to, and that would have caused problems, right? So to avoid this, we add an extra table called a hash table. So the long and short of it, to summarize, is that an inverted page table has some benefits in the sense that we do not need a separate page table per process. We can have one page table for the entire system, but however, accessing it is complicated. So let's now summarize the entire memory access process. So we have the processor that releases virtual addresses. We have a memory management unit, page tables are a part of it, that translates the virtual address to physical addresses, and these are sent to the caches. So pretty much every access needs to go through the MMU. So what we have described up till now, we need to access the page tables, which themselves, so where are the page tables stored? Well, the page tables have to be stored somewhere and they need to be stored in memory, right? We can't have a separate piece of hardware for them. So they need to be stored in memory as well. And so they, of course, will be stored, at some point, and the physical addresses will be known. But nevertheless, this will make things very slow because for one load instruction, we'll have to walk the page table. So the term is walking the page table, right? Let me just write it. So let us, design a fast mechanism such that we don't have to access the page table for every single memory access. So what we can do is that we can have a very small cache that has the end most recent mappings. So due to temporal and spatial locality, we should observe a very high hit rate in this cache, and we will not need to access the page tables very frequently. So we add a specialized structure called a TLB. So TLB is a translation look aside buffer. So pretty much it stores translations. So TLB is actually a very small cache. It's typically a set associative or a fully associative 64 entries cache. So what comes in is actually the page number, and we quickly access the TLB, and what comes out is the frame number. All right. And since the TLB is a very small structure and it uses the LRU replacement scheme, right? So it stores the most, recently used entries. It can satisfy most of the translation requirements of memory addresses. So TLBs typically have a very high hit rate. The hit rate of TLBs can well exceed 97, 98, 99%. So most of the accesses actually hit in the TLB. So TLB miss rate per se is not that big a deal. And this ensures that we can access our caches very, very quickly. This is because our translation operation is very fast. And for one of those occasional TLB misses where we don't find the page number in our TLB, we need to access the page tables and we need to get the translation from the page tables, populate our TLB and move on. So the TLB can be thought of as a cache for the page table. It helps speed up the process of memory address translation, and the reason it works is because of spatial and temporal locality. Right? Well, spatial, well, okay, both. Temporal locality because we'll reuse the same pages over and over again, and spatial locality because there's a high probability that we'll remain within the same page. The page is a huge structure, it's 4 kilobytes. So the TLB can be a fully associative cache, it can be a set associative cache, no problem. Each entry will contain a page to frame mapping. A TLB typically contains 64 entries, can be 128 also, no problem. And accesses, so if there is no, so then if there's a TLB miss, we go to the page table. And it is possible that if you are accessing a page for the first time, we will not have a mapping for it. So this is called a page fault, right? So what's a page fault? A page fault is when the page is not available in memory. So we'll see it can happen because of various reasons. So one of the reasons can be that we don't find an entry for it in the page tables. So in this case, whenever there is a page fault, we need to create a mapping, right? Allocate an empty frame in memory and also update the list of empty frames. So mind you, in the memory management unit, which can be implemented either in hardware or in software, we need to have a list of empty frames. So the moment we take a frame out of this list, we need to update this list, pretty much remove that frame. So now let's consider a new term called swap space. So let us consider a system with 500 megabytes of main memory. So the question that we ask is, can we run a program that requires 1 gigabyte of main memory, right? So let's look at it. 1 gigabyte of should not be main memory, but should be memory actually. So let us assume that we have a system where we have a processor, we have an L1, we have an L2, and then we have our main memory, and the caches are inclusive, and the size of the main memory is 500 megabytes. But our program is huge, so it actually accesses 1000 megabytes or 1 GB of main memory. 1 GB of memory is what it requires. Can we run our program on such a system? Well, so the answer, as it turns out, is yes. Because if we do not allow this, we'll be really constraining our program, and we'll also need to invest in a lot of memory. So it's a better idea to have some way of doing this. So what we can do is that we can add an additional entry in the page table. So this will be an additional bit. It will say, is the frame found, is this particular frame found in main memory or somewhere else? So, the page table, so what does a page table entry look like, or a TLB entry? Given a page number, it will contain the frame number. But what we are suggesting is that we can have a little bit more, or we can have some more data as well. So we can have some amount of state that says that is this frame available in main memory? Sorry, M. Or is it available somewhere else? Or is it available somewhere else? So in this case, we can add more, memory-like storage devices to our system. And when we are translating from a virtual page to a physical frame, we can specify in exactly which storage device will you find this physical frame. So one of the possible storage devices is main memory, but we can have others as well. So let's consider the hard disk. So almost all computers have a hard disk. So we will study the hard disk later in chapter 12. But for beginners, it's a magnetic disk that stores data. If the main memory is something of the tune of 8 gigabytes or 16 gigabytes, the hard disk is much more. It's typically 500 gigabytes or 1 terabyte. So it's much larger, but it does not use semiconductors. It uses magnetic storage. So it is much slower, much slower. So we can say that the hard disk can contain a dedicated area inside it called the swap space, right? So in the swap space, we can save some frames which are not fitting in main memory, so they can be saved in the swap space. So a conceptual diagram of this would be that we have the processor, then we have the L1 cache, we have the L2 cache. Below the L2 cache, we have the main memory. This we are saying is somewhat constrained. So if we need some additional space, we can go to the hard disk, which is the biggest storage structure that we have on machines. And a part of it we can dedicate to actually storing some of the frames that are not fitting in main memory. So in this case, the physical memory, right, the physical storage area becomes a combination of the main memory and the swap space, right? It's a combination of this and that. Clearly the main memory part is much faster, but we can still get little bit of additional storage in the swap space. So what each page table entry will contain is that it will contain the frame number and it will contain a bit, right? So the bit, if it is 0, it can say that the frame is there in main memory. If it is 1, it can indicate that the frame is there in swap space. So let us now look at a flowchart, right, of a typical memory access. See, if we have a memory access, can be a load or store, does not matter. So is it a TLB hit? Well and good. That's the best case. Yes. So we send the mapping to the processor, we construct the physical address, and we send it to the memory system. If there is no TLB hit, we check the page tables. If there is a hit in the page table, then we populate the TLB with a new mapping, and we also send the mapping to the processor such that it can create a physical address. Now, if there is no page table hit, if this mapping is not there in the page table, so if you don't find an entry in the page table, this means that there is no mapping, so a mapping needs to be created. So what we do is that we check if a free frame is available in main memory, right? In our frame list. Well, if it's available, yes and good, we go to this stage. Otherwise, if it's not available, we go to main memory and we evict a frame to swap space, right? So we're assuming that we have main memory, and so the L2 cache is connected to the main memory, and the main memory is connected to the hard disk, which is huge. So part of this is, let's say, the swap space. Let me call it SS. So we take one frame in main memory and we essentially kick it out and put it in the swap space. We also update the page table for that frame, saying that it's in the swap space. And then we read in the new frame. So if let's say new frame has some data in the swap space, what we can do is that we can either create an empty frame, or if we know what its content should be, we read in that from the hard disk. And then we create and update the mapping in the page table. We populate the TLB and we send the mapping to the processor. All right, and the processor can use this mapping to create to create a physical address and send it to the memory system. Now let's take a look at some of the advanced features that are possible. So with our paging and virtual memory setup, so sometimes it is necessary for two processes to actually share data. And mind you, this is purposeful, this is deliberate, that sometimes it might be necessary that for process 1 to send some data to process 2. So when will this be necessary? Well, we can think of a producer-consumer situation, that we have, let's say, one process which is accepting requests from the web. So this is P1, it is accepting requests from the web. Then we have a process P2 which will get the request from process P1. P2 will access some database, give some data to process P1, and P1 will send the data back to the client over the net, over the web, right? Over a network link. So in this case, P1 and P2 need to share some data, and this can easily be done with our mechanism. What we can do is, for the same physical frame, we can map it to two separate pages. One page is in the address space of process P1 and one page is in the address space of process P2. So if process P2 writes to this page, it is actually writing to this physical frame. Similarly, if process P1 writes to this page, it is writing to the same physical frame. So in this way, kind of indirectly, they can share data. So if P2 writes something over here, is the same memory locations that P1 can access, so P1 can read the values. So implementing shared memory in this way is very, very common, and it's extremely common to use virtual memory for creating mechanisms for processes to share data. Another thing is that let's assume that we want to protect some regions of the program and we don't want them to be modified. So one such section that can be protected is the text section, which is where the instructions of the program are there, right? And we don't want the instructions to be modified, because if somebody modifies the instructions, it's like inserting a virus. So let's say if I modify these instructions and I make them send random emails to random people on the net, that's going to create problems. So we want the program to be unmodifiable. So how do we do this? Well, the simple way is that we extend each page table entry or TLB entry with the frame number. It can have some additional data. And we also add a read-only bit. If the read-only bit is set to 1, means that no other process can actually write to this memory region. Just in case you're able to break into a program, it ensures that even the same process cannot write into this region. Essentially the text of the program, the instructions of the program cannot be modified. So this is one way of ensuring protection and security in a virtual memory system, that we can mark large parts of the memory space as read-only, which means that once it is, it can only be read for the first time. It can only be written the first time it is initialized. After that, no process can write to it. And this ensures that our programs remain the way they are and they are not maliciously modified. Alright, so this brings us to the end of the memory systems chapter. So we are done with memory systems. So we are all ready to take on chapter number 11, which is the chapter on parallel programming and multiprocessor systems.